Okay, so we found appropriate reviewing window right here. First of all, we found, someone set it at this right here, -1 for the X-min, 2 for the X-max, -5 for the Y-min, or 7 for the Y-max. That gave us all the key features that we need to see. You guys, right here, attention right here. Okay, now, and I just got through telling you, and I'm going to say this for those people who are listening to this at home, that the maximum number of real zeros can be determined by the degree of the polynomial function. What that means is that since this is a degree 3 right here, the most number of real zeros, in other words, the most number of times it can cross the x-axis is 3 times. If you'll notice over here on this graph, we see 3 times it crosses. So we know for sure that that's the number of times that it can cross. Noah? Yes. Okay, Noah asked, does that mean you can cross less than that? And that's what I was just going to talk about. Your first problem yesterday was an x cubed function, wasn't it? And I want to talk about this too, because your function yesterday went like this, okay? And it only crossed, how many times did it cross the x-axis? 1 time, right? So the x-axis is somewhere like this. I can't remember. Okay, well, that's a good question. How do you find a minimum and maximum out of that? There are no minimums or maximums on this problem. Because now listen to this second part I'm going to tell you guys. The most number of turning points, everybody write this down. A turning point is a min or a max, by the way. The most number of turning points, if you want to write on a polynomial function, but your notes that I gave you, your vocabulary that I gave you has that on there already, but the most number of turning points that a polynomial function can have is 1 less than the degree of the function. In other words, since this is degree 3, what's 1 less than degree 3? What's 1 less than 3? 2. 1 less than the degree of the function. The most number of turning points a polynomial function can have is 1 less than the degree of the function. So since this is of degree 3, it can have at most how many turning points? 2. And a turning point is what? A minimum or a maximum. Okay, now the one that we have graphed right here has how many turning points? Okay, has, well, look at it again. How many turning points? 2. What are they? Okay, that maximum and that minimum right there, right? So we have that one. In contrast to that one I gave you guys yesterday, it looks like this. It has no turning points. But this is what I wanted to show you right here. This one has what we call 2 inflection points. It's kind of turning, but it's not a minimum or a maximum, is it? And it's kind of turning right here. So we have an inflection point right here. We have an inflection point right here. The graph is curving. It's curving right here, and then it curves back up. So if you see those inflection points, those are kind of like turning points. So it's not going to have any other turning points. It's either going to have inflection points or turning points. Okay, so if you see those inflection points, you know you see the important features of that graph. So you don't have to go hunting. You don't have to start expanding your window out and trying to find those other turning points. Okay, you know that you have them all. Okay, any other questions about that? Okay, what I want you to do right now, well, let's finish talking about, there was a couple of those items I didn't finish talking about yesterday, right? Or last time? What were the last 2? Oh, go, yeah, I thought you were just...
Oh, you're good. No, I know. Wander in. Students of this must be your advanced class.
Okay, going back to the Bell work problem. Okay, so we have to find end behavior and multiplicity. Well, you guys, look at that vocab list I just gave you. What does it say about multiplicity? Multiple roots. A root, you guys, is as far as we're concerned right now, a root is the x and y, the x-intercepts. So this is a root. Where does that root occur at? What'd you guys get for that one? Say that again. 1.276 comma what? 1.382? Do we need to do this one? Okay, let's do this one. Remember, you hit second in the trace button, bring up the calc menu. We're looking for a 0, which is number 2, right? We go to number 2, and we use the right and left arrow keys to move over there. Okay, right there, I'm looking for a left bound, right? So am I to the left of the point right there, where it intersects? Yeah. So I have right here is my intersection point, and right down here is my cursor. If I go straight up to the x-axis, I'm to the left of that point. So that's a left bound. I hit enter. It marks it with an arrow up there. Now it's asking me for a right bound, so I've got to go to the right of the 0. And by the way, you guys, a 0 and a root are the same things, Trevor. It doesn't matter if you got this window, you should still get the same 0, approximately. It might be a couple, you know, when you start rounding the numbers, they might be slightly off if you have a different window, because it's not narrowed in as much, but you should be somewhere around right there, 1.382, if you round it. 1.382. Did anybody have a different window and get something different? Yeah. What did you get? 1276, really? That's way too far off. 1276. Okay. Let me just see. I want to see if it's that far off, because so we're finding these zeros right here. I can find another one. Notice this time, you guys, to be left of this point, I have to be up above it because it's slanting down left to right over here. So there's my left bound. There's my right bound. .711 is going to be my 0. 0.711. Okay, you go second and hit the trace button. You're in the calc menu, right? You're looking for a 0 where it crosses the x-axis. It's an x-intercept. Got it? Okay. So we got that. And you put in your left bound, your right bound. I'm going to go clear over to this one now. Do this one. Okay, there's my left bound. There's my right bound. And negative 0.509 is what I got. So, okay, so there's my zeros, or my roots. Okay, I need to talk about multiplicity. You guys, multiplicity refers to a root or a 0 happening more than once. Let me tell you when that happens. When you have a graph that comes down, let's say this is positive 2 right here. Let's say the graph comes down and touches at positive 2 and goes back up. Okay, can do something else over here. Say it did something like that. 2 is actually what we call multiple 0. It actually is going to happen twice. They call it a multiple. They call it a 0 of multiplicity 2. Okay? So sometimes that happens on some of these graphs. We'll come down and just touch it right there. Okay, if I was to factor this one right here, you guys, into its factors, it would have 3 factors. However, these 3 factors, since these numbers right here are zeros, none of them are rational numbers. They're all irrational numbers. I can't give you a integer over here to put right here as x plus something, x minus something. But would happen in this one right here is x minus 2 would happen twice. And then let's say it crossed at negative 1 over there. So x plus 1 would be, that's not for this one right here. Okay, it's for a different one, but that would be one of multiplicity 2 because 2 occurs twice. If a factor happens 3 times, the solution happens 3 times, then we say multiplicity 3. Okay, any questions on that? So could you create a polynomial equation that had multiplicity 3? What would be an example of that, JD? What do you think? What would be an example of a polynomial equation with multiplicity 3? How could we come up with one? How could you come up with a polynomial equation of multiplicity 3? In other words, it has to have the same 0 3 times. In other words, it would have to have the same factor 3 times, right? So it would have to have, choose a number, choose an integer, 5. We would have to have something like this. F of x equals x minus 5 times x minus 5 times x minus 5. If I multiplied all those together and expanded it out, I would have a polynomial function that had multiplicity 3 because these are going to all cross. I mean, the only real 0 is going to be at 5. It's going to either touch or cross right there at 5. Okay? So that's what that means. All right, last one. End behavior. I want to talk about end behavior of this function that I just crossed out right here. End behavior. Look on your paper I just handed out to you. What does it say end behavior is? As x goes to infinity, right? Or negative infinity. Look right here on this one. As this function as x is going to the right, as we're getting larger, what's happening to this function? What's it doing? It's going up. It's increasing. It's going up, isn't it? Okay? So this function, the end behavior, it goes up to the right. That's how I would describe this one. This one goes up to the right. So if I'm talking about end behavior, up to the right. Okay? And wait, what happens as it goes to negative infinity? What happens as we're going this way? Okay, the graph is going down to the left. Down to the left. Now, I actually can tell by looking at this polynomial function without ever seeing its graph what the end behavior is going to be. Okay? You guys want to investigate that a little bit? Okay? I'm going to do this right here. I want you to put the following functions in here. Okay, everybody put this in. Under y1, I want you to put negative x cubed minus 3x minus 2. Okay? And negative x cubed plus 4x plus 3. And on y sub 3, negative x cubed plus x squared minus 2x plus 1. I want you to put all 3 of those in. I want you to tell me what you see about the end behavior. Discuss it in your groups. I'll give you a second. Go. Okay, let's look at this one right here. What did you notice about the end behavior of all 3 of these?
They're all going down.
Well, as you go to the right, what are they all doing?
Down.
They're all going down to the right? Okay, so you're saying they're all going, as you go to the right, it's going down, right? What about as you go to the left? As we go to the left, it's going up. So it's down to the right and up to the left, right? Well, look at this. What's similar about all 3 of these right here that might be causing that? Yeah, this negative right here. If, okay, now the third, what does the third do? Okay, let's do this. Now I want you to do these right here, because I want you guys to notice that if the degree is an odd number compared to when it's an even number, what happens, okay? And notice when this is negative compared to that first one we did a little bit ago. Like this one over here, y equals was positive number right here, 12, instead of a negative number, right? Okay, so, and it went up to the right and down to the left, but when all of a sudden it's negative, it went down to the right and up to the left, okay? So what I want you to do now is type in the following graphs right here. Under y1, I want you to go x to the 4th minus 3x squared minus 2, and 2x to the 4th plus 5x minus 4. Tell me, what do you notice about those two graphs? Okay, Carly says it's going up to the left and to the right. Okay, so how is, when this is x to the 4th, how is this different than if it's x cubed? Okay, it makes it go up. Do this now. Do this. Make that a negative. Do you guys know how to insert a negative? Do you guys see above the, on my calculator right here, see above the delete button, it says INS? That means insert. So hit second and that delete button, and you can insert a negative right there. And do a negative right here on that one. What happens to your two graphs? Okay, so they flip upside down. Okay, so what are the things that, and so what's the end behavior on those doing? So as you go to the right, what's it doing? As you go to the left, what's it doing? Okay, so it's going down to the right and to the left, right? Okay, so little test here. See if you guys understand this. Okay, without graphing this in your calculator, okay, and without saying it out loud, I don't want anybody to say it out loud. For the first 30 seconds, I want everybody to think about it, and then I want you to discuss it at your table what you think it is, okay? All right, don't look here. Okay, without saying anything out loud, I want you to tell what the end behavior is going to be. What is the end behavior going to be? Okay, now discuss in your groups. What is the end behavior going to be without graphing it in your calculator? Okay, Trayson, what does your group think it is? Let's go on. Let's go to Cole's group. Cole, what do you guys think it is? Well, what do you mean? As we go to the right, which way? Is it going up or down? As x goes to infinity, what's y doing? It's going down. As x goes to negative infinity, what is y doing? It's going down. Cheyenne says it's going down both ways. She says the end behavior is like this. I don't know what it does in between. Does it make a W? Upside down W or an M? Or does it just go like this? Big problem. Either way, if this coefficient is negative, and this is an even number, then, okay, if it's an even number, they're both either going to be going up or down, right? If it's negative, it's going to be going down. Positive, it's going to be going up. Yeah, because you guys remember when we learned about quadratics? Because this is negative, which way is my parabola going to be opening? Down, right? So anytime the power is an even number, you might want to write this down. When the power is an even number, They'll both be going up or both be going down. A negative will make it go down, right? Okay. If the power is even, they'll either both go up or down, depending on whether it's positive or negative. Say that again. Was it? Well, no, the last one, that was a negative 5x to the fourth. So since it's even, they're both either going to be going up or down. Since it's negative, I mean, since the power is even, they're both either going up or down, right? If it's negative, they're both going down. Okay, let's look at this one. You guys, without discussing this, everybody think to themselves first. Give everybody a chance to think on this one. What's the end behavior of this one right here? I'm going to let everybody look at it for a second. After you get through looking at it, it says negative 5x plus 4x cubed minus 6x. Okay, now discuss in your group. What's the end behavior of this one going to be? Okay, ask. Say that again. Well, I kind of tricked you guys on this one, right? What's the highest degree term? It's this term right here, right? That's the only one you're going to be concerned with if we're looking at end behavior. Okay? So, since this is an odd number, what do we learn from an odd number? Yeah, one's going up, one's going down. Since the coefficient of this x cubed is a positive number, positive 4 in this case, then what's it doing? Down to the left and up to the right. Are we getting that? How many of you guys are starting to get that? Okay. Here we go. End behavior right here. I want you guys to all look at this right here. Don't say it out loud. I'm going to give you 4 of them. This is like a little quiz. Everybody write it down. You're going to either say up the left, up to the right, down the left, down the right, up the left, down the right, or down to the left and up to the right. You're going to say that on all of them. Okay? Ready? All right. There's 4 of them. See if you can come up with the end behavior on all 4 of those. Yeah, you can do it. That's where I want you to do it in your notes. What's this one? Here's my highest degree term right here, right? It's odd, so it's going to be going either like this or like this. Since it's negative, it's going to be going down this way, right? Up to the left, down to the right. Okay, this one right here, highest degree term, right there. And so it's either going to be both going up or down. Since it's positive, they're both going to be going up. This one right here, the highest degree term, that one. Since it's odd, it's going to go either like this or this. And since the coefficient is a positive number, it's going to be going like that, right? Up to the right, down to the left. Last one. Okay? It's the power is even, so it's either both be going up or both being going down. Since it's negative, they're both going down. Think you guys got M behavior down? So, huh? Yep, you did it right. Okay, now, some of you guys are saying you still don't understand multiplicity, so I want to talk about multiplicity. All right, if I multiplied this out, okay, I have three factors right here. This one right here, you guys, has multiplicity 2. This has multiplicity 2. The reason being is because this factor right here and this factor right here are the same. The question is how can you tell when it's not written factored out form? Okay, so I'm gonna times them together right now. If I times this binomial by that binomial, I'd get x squared plus 2x plus 1. And then I would have to still times it by the x minus 3. Okay, you guys don't copy this down right now. I'll give you a second to copy down a second. I want you to watch and listen, okay? If I multiply these two together, you guys all know how to multiply these together, right? Yeah. Okay? You got to, you can't say FOIL on this. You got to use a distributive property. You got to multiply this x. You got to distribute the x. And then you got to distribute the 3, right? The negative 3. Like that. Okay? So if I go the x, I'm going to times the x by the x squared first. So x times x squared is x cubed. X times 2x is 2x squared. And x times 1 is x. And then negative 3 times x squared is negative 3x squared. Negative 3 times 2x is negative 6x. And negative 3 times 1 is negative 3. Okay? And if I add like terms, I get x cubed minus, right? The 2x squared and the minus 3x squared makes negative x squared. The x minus 6x is negative 5x minus 3. Here's my function if I multiply it out, okay? Now, everybody go to your calculator, and we're going to put it in there. I do want you to put this into your calculator right now. Clear this one out, and we're going to put in x cubed minus x squared minus 5x minus 3. And we're going to hit zoom 6 to graph it. Do we see everything here? I'm going to zoom in a little bit, though. But I'm not going to use my zoom in feature. I'm going to go to my window. I'm going to come into negative 4 and positive 4 on this side. And then I'm going to come in, down from the top just a little bit. My y max is going to come down a little bit. So I'm going to go to my window. And I'm going to go negative 4 to positive 4. And then I'm going to change my y max to about, actually I'm going to change it to about 4. Okay, there's my window I'm going to use. And I'm going to look at this graph a little bit closer. Okay, what is happening at negative 1? Does this graph, it touches it, right? It touches it because see these two factors up here, this x plus 1 and this x plus 1? They occurred twice. And I know you guys are saying, well, that's a positive 1, and this is over here is a negative 1. But remember, when you're solving an equation, you set each factor equal to 0, right? And you solve each of those equations. I minus 1 from both sides of this one, and I get a negative 1, right? And over here, I add 3 to both sides, and I get x equals 3. And so, my solutions are negative 1 and 3. Well, if you look right here, it touches at negative 1, and it crosses through positive 3. Those are my two solutions. But the solution negative 1 is of multiplicity 2. It's of multiplicity 2 because it happens twice. JD. the factor happens twice, but it only touches one time, right there at -1. But we call it multiplicity 2 because the factor happens twice. How do you know by just looking at the graph? Well, if you'd have to come in and see if it just touches, because we'd have to probably zoom in even more. I know for sure this one just touches because I can see the factors right there. This one's really hard to tell unless you look at the factors. But if you can see it looking like it's touching, you can kind of guess that, hey, it might be a double factor. It might be happening twice. It might have multiplicity 2. Okay, Trayson. No. You know what? Let's look at a multiplicity 3. Should we do that? Okay, let's do that one. Let's take, it's a good idea. Let's take this function, f of x equals x minus 2. Let's do this one, x minus 2 and x minus 2. We'll just do it so it has x minus 2 3 times to make it simple. Okay? So if I multiply these two together, these first two together, I'm going to get x squared minus 4x plus 4. And then I've got to times it by the x minus 2. Okay, so I distribute through like we did last time. I'm going to get x cubed minus 4x squared plus 4x. All I did is I just times that by that, and then that. I distributed the x, right? Now if I distribute the 2, I get minus 2x squared plus 8x minus 8. If I combine like terms, I get x cubed minus 6x squared, is that right? Plus 12x minus 8. Did anybody see any mistakes I might have made? Because sometimes I do that. Anybody see any? Because if we go to graph this and I made some mistakes, we'll be wondering what's up. Everybody got that? Okay, let's graph it in the calculator and see what it looks like on a graph. Should we do that? So x cubed minus 6x squared plus 12x minus 8. Whoops. Okay, so I'm going to hit zoom 6 to graph it initially. Okay, we're going to have to really zoom in on that, aren't we? You want me to show you another cool feature? Want me to show you a cool feature of this thing? We have a zoom box that's kind of cool. Everybody hit your zoom button. And box number 1. Where's my cursor? It's right at 0, 0. What I'm going to do, I'm going to zoom in on this part right here. I'm going to get my cursor right there and I hit enter. And what it does is I now go down, and then I go to the right, and it makes a box. This is harder than those droids that you guys have out there, by the way. So, just kidding. It's not as hard. Okay. You hit zoom box. Did you do that? Zoom, and then number 1 is box. Okay. And you move your cursor should be at 0, 0. You move it to the one corner of your box, and then you hit the up, then you hit enter, and you hit the up key or the down key, and then the right key or the left key. So you make your box. Hit enter, and it will zoom in on that area. Now it looks like to me it's just crossing at +2, right? So in this case, since it's cubic function, it has to cross, but it's a multiplicity. It's a multiplicity 3, right? Because the factor, we saw that the factor occurred. So you wouldn't be able to tell this one by just looking at the function. Actually, there is something that can tell us that. I know enough information. Let me tell you what I know. Okay, I know this. I know that a cubic function, since the end behavior, it has to go up one way and down the other way. And I know it's got to go up to the right and down to the left. I know it can have at most 2 turning points. I also know that the number of real zeros either has to be 1 or 3. Okay, I know that. And so when it crosses right here, well, actually, I wouldn't know if it had 1 or 3. So the other two could be imaginary zeros. We'd have to see it in factored form to do it, which we can see right here, but usually you can't. I'm guessing that it would, if it was an odd number of times, it would just cross. It would cross at one time at 2. But if it was 14 times, I'm guessing it would touch it 2 and go back down. That's what my guess is. Okay? So it looks like if it touches it, if it's an even power and it touches it, it could be multiplicity 2, 4, 6, 8, 10, 12, 14, whatever. If it's a multiplicity of odd, if it's an odd function, it has an odd degree, then it looks like the multiplicity, if it crosses it, could be more than that. We would have to have it in factor form to tell. You're not going to be able to tell the multiplicity on all these, okay, until we do some other stuff later in class this year, okay? This is your assignment today, then. I'm going to add a couple problems to it. See these 5 problems right here? 2 of them are two of those problems I gave you already. Which numbers did I give you already? Did I give you 1 or 2? I gave you one of those 2. I gave you 2. So we've already done 2 on that paper, and I gave you either 3. I think I gave you. Did I give you 3? So your assignment today is to do 1, 4, and 5. I'm going to add that onto your assignment. Okay? I want you to do the same stuff that I asked on here. I want you to graph it, and I want you to find an appropriate viewing window. I want you to identify any minimums or maximums it had, that some of them might not have any. And I want you to identify the domain and range. I want you to identify the intervals on which it's increasing or decreasing. And I want you to approximate the roots. The roots, remember, the roots are the zeros, the real zeros where it crosses. We'll talk about imaginary zeros later. And then I want you to describe the end behavior on all of them. Yeah, if you guys want to take a picture of this, go ahead. Yeah. Okay, you guys, on that vocab list, I wrote down some information about domain and range. So get this out. Everybody get this out. Carissa, get this out. Okay, domain says the set of all values that the independent variable or the x variable takes on, right? And the range is all the y ones. Well, because on a polynomial function, and I wrote down the definition of polynomial function up there, and I was going to give you some examples here, but a polynomial function is continuous, which means it's not going to have any breaks in it. Once you start drawing this thing, it goes on forever, okay? And it's always going to be curvy like this, and it's never going to go back like this, right? Because then it wouldn't be a function, okay? So all polynomial functions are going to be like this. Now, linear functions, linear is a polynomial function. A quadratic is a polynomial function. You can write this down up above there, or I think I did. A cubic or a quartic. A quartic is a 4th degree polynomial, right? A 5th degree, a 6th degree, a 7th degree, it doesn't matter what degree it is. The polynomial function. Guess what the domain of every polynomial function is going to be? It's going to be all real numbers because it goes forever, doesn't it? And it can't curve back, so the only way it can go is forever right and forever left. Okay? So the domain of all polynomial functions is going to be all real numbers. You can write it like this as negative infinity to positive infinity, or you can write all real numbers. Either way, okay? Now, think about the range. Is the range always going to be all real numbers? Which of the functions is the range not going to be all real numbers? Think about end behavior, you guys. A quadratic. Why not a quadratic? Because it goes like this, and it goes back down. And so the highest point it's going to reach is right there. Well, it depends on where it is, because I mean, if this is your XY axis and it was going like that, the highest Y point is that point right there, right? So whatever the highest Y point is, that's if it's opening up, down, right? What other kinds of functions are going to be restricted? Yeah, the W one, the quartic, the fourth degree polynomial, right? In fact, how could we say it to include them all? If it's of what degree? Not positive. Even degree. If it's of even degree, you meant that, didn't you? I used to always do that too. If it's of even degree, then it's going to be either opening up. Both sides are going to be going. N behaviors are going to be up, or it's going to be down. And so your range can, if it's going up, your range is going to be from the lowest number, your lowest minimum, up. If it's opening down, it's going to be from your highest maximum and down, right? That's the range. You just look at the Y numbers of your highest maximum and down. Now, what if it's an odd degree? What if it's odd degree? The range is going to be all random because it's going up one way and down. It's going up forever one way and down forever in the other way, right? It can either be going like that or like this, okay? So we got that down? So the domain and range you should be able to look at it. You should be able to look at the function without even graphing it until the domain and range. Does that make sense? Because you can look at the end behavior, and that's going to tell you the domain and range. Got it? Okay.